right, welcome to the second lecture on performance computing for physical systems. First, a few admin things. I have still to confirm some of you. I will do this after the lecture, the one that requested it per email. If you're confirmed, just ignore what I said. The lab sessions, I know that some of you were here and the class was occupied and you went downstairs in the basement. That's where it will be from now on. I will update Moodle. I will advise, tell everybody that basically 2 p.m. on Wednesday in the basement lab. All right. If you cannot follow the lab, inform me private. I know that there's a couple of people who have, for example, conflicts. We'll find again a solution, and you can use, for example, for questions that you have about in general the class or the project itself, we can use the office hours to compensate for the lab. So that is a solution. What else? The lectures are posted online, so if you miss them, you can see them there. The lecture notes are also there, and there's a bit more information in Moodle about the course. If you're I don't think we have anything else. So, summary of the lecture. By the way, any particular question about last lecture before we actually go into the summary or into the next topics? If you want to discuss it. Good. So, in last lecture we saw Python fundamentals and how to create procedures in Python. We also looked at just a very quick introduction to what functional programming is and to object-oriented programming. We also looked at the fact that Python has multiple inheritance and what we can do with multiple inheritance by basically using mixing to encapsulate multiple functionalities in different classes and then adding them to the classes that we produce on a need-to-need basis. And then we looked at some design patterns that we will see all over the class again and again. Singletons, factory methods, basically creation of patterns, so how to create objects from instead of just calling the class, but in a particular way that, for example, singleton assures that there is only one instance of that class running around. And for factory methods, in a way that you can basically configure the objects before you give them back to the programmer that is using your library. Structural patterns like decorators, which are very useful to encapsulate functionality in something that takes your class, modifies it, and then returns it back to you. For example, with authentication or with other particular functionality that you encapsulate in the decorator. A proxy, we'll see one today again, which basically is an object that is a shallow object but is connecting to some functionality behind the scenes and is returning the data on demand by accessing this functionality behind the scenes. Could be a database, for example. And then we looked into commands, observer, and template methods that basically are behavioral patterns. So commands encapsulate the complete, and we'll see that again today, an example of it, and encapsulate the data, the action in one single object that can be passed to something to be executed. We saw the example of a button that takes the command to turn on the light or turn off the light, which is a bit of a made up example, but it shows the concept. The observer, where there is actually an object that is basically registering to observe events that happen in another object. And this way the producer of the events doesn't have to know that the observer is listening, but it just produces the events, and the observer has the capability of registering itself and registering itself. And then the template method, where basically you create functionality, and then you leave part of this functionality to implement for the programmer that is using your libraries. And the programmer, it doesn't have to know about how you implemented the functionality, just has to implement this part of the deal. And then in your basic functionality, you call this implementation from the programmer, and you let it run. Today we'll look into objects and class lifecycle. So we saw how to create an object, how to create a class. Today we'll see what happens when you actually create a class. First of all, what happens when you create an object. So The object lifecycle starts when you call, for example, class user with double brackets, and at that point, the class is called, or specifically the method __new __ of the class is called. This method is there to allocate space in memory for your object, to do the minimal structural organization so that there is an object that can be called an object there for you to access. Then the next part is the init method gets called. Usually you don't, you rarely write the new method. The new method is implemented in Python itself, the standard one, but you might need to access it sometime. But usually you implement the init method. The init method is one of this template method, basically. It's there so that you can implement your own initialization of the class and therefore of the object. So you create all your object variables and initialize some of those there and so on. So once this is called and the object is set up, then you use it. You basically call the methods, you change the states and so on until you're done. And then at some point, but we don't know when, the garbage collector will call dead. Once your object is run out of scope, you don't have any reference to it anymore, then at some point the garbage collector will destroy it. And by destroying it, we'll deallocate the memory, we release anything that the object is using behind the scenes. So this is what the object lifecycle looks like. The same happens for a class, because a class in Python is an object, all right? So what is the class an object of? A class is an instance of the class type, which is a very special class, which is implemented directly in the Python interpreter. So you cannot implement your own type, but we'll see you can implement something similar. So when you create a class, you write def user and everything else that is inside, what happens really is that the type super class, let's call it meta class, which is what it is, type is going to be called with new, and it's going to allocate memory for that class. Because again, class is an object, so you can use it as an object. And it will allocate memory, it will create the object in itself in memory, will return a class object. And then type will also be called with init. And this will create the initialization of the class itself. Like for example, it will put the class variables there instead of the instance variable, like the variable that are shared by every instance of the class, and that can be changed by every instance, but it will have only one value for the whole class. Then there is a particular thing that doesn't happen for objects. There is a method that is called init subclasses. So if you have, for example, in the example of last time, user and employee, if you have an employee class, from the user class, you can control what happens when somebody creates a subclass of you, like the employee. And you can say, for example, you can enforce that the name of the user is not overridden. You can enforce that it has at least other 5 attributes. You can do whatever you want. You are basically, you can implement this method to control what the subclasses do. We'll see an example of how to use it. And then in the end, you can just use the class. The class uses, in this case, object creation, of course, static methods, class methods, everything that is implemented in the class type. Questions about this? Yes.
So do you mean this life cycle will go on during the definition of the class without instantiation?
Yes, this is this is a kind of instantiation, but instantiation of the class itself, right? So again, classes are objects in Python. Functions are objects in Python. Everything is an object in Python, basically except type, because it's a special object, but everything else is an object. So it's the instantiation of the class. Once you have the class in memory, then you can instantiate objects, right? From the class, so implemented by the class. Usually you don't see this process. It's done behind the scene for you. And there is no del for classes. I mean, it's taken care of by the interpreter and shut down. So why am I telling you this? Because, for example, if you want to, let's say, implement a object relational management. Have you ever heard about object relational management? No, okay. So if you have a database, what do you use to communicate with the database? SQL, ever heard about it? Okay. So this is a special language, right? You use it, you select data from a table, you return a list of rows and columns, right? And you can insert data, you can update data, and so on and so forth, right? But this is not, it's nothing to do with object-oriented programming, right? It's a scripting language, and it returns just tables. So somebody thought, wouldn't it be nice to access data in a database with objects? Like, I mean, instead of accessing the table user and select a user one by one from the table, I can create an object user, class user, and then when I instance one object from that class, I'm basically referring to one row in the table. And I can do all the operations on the object, and they will be automatically saved to the database, right? If you want to implement something like this, you kind of need to dynamically create classes. I mean, you can do it also statically. It's just basically a lot of typing because you have to reproduce all the structures that are in the database in code. But if you want to do this dynamically, you can do it basically by using init as subclass. I mean, we can find how it's done in detail. But in general, what you want to do is when somebody inits, let's say you create an object which is called db object, right? And you subclass this with a class called user. The first thing you want to do is find the table with the name user. Then, once you have found it, you can create attributes for every column directly. So the class user doesn't have to implement anything. You can implement it dynamically in init subclasses when you call it, when you create the class for the first time. Let's see a demo of this and see how this works. So, can you read this? All right, so what am I doing here? I define the class db object, and basically what I'm doing is I'm defining init subclasses. No, so this method is going to be called whenever I subclass of db object. And what it's doing is doing a few things. First of all, is making sure that anything that is done for me by the Python interpreter, by my other superclasses, it's still be done, right? So I call super init subclasses with all the arguments that I get. That I'm good. Then I'm creating a connection to the database, and I am saving in my class. So this is the subclass this is user, right? In this case, this is the class that I'm creating. I'm saving table name as my class name, so user, lower, so lower user basically, right? I'm saving it here. And then I'm calling a setup table definition, which is going to basically query the database and see what is this table about. And this is a special method that it's called @exit. I register this class to close the connection. This makes sure that whenever I exit basically this class and this goes out of scope, the connection is getting closed, right? So I'm doing some basically management of my resources. So what is setup the table definition does? This is the next function, and I can actually give it like that. So what it does is it retrieves. Now this is a special SQL here that I'm doing. Pragma table info. I'm just calling the info on the table called user in this case, right? Because I just saved it in class table name. So I'm using it and I'm retrieving the information about this table. Then I'm just going through each column and I am adding an attribute here, an attribute to the class for every column that I have. So I'm dynamically generating the structure of the class. So when you then access user, you can say user.name, and this name was created here, right? Do you understand the structure of this? Right, so the alternative to this would be to write class user and then write name, and then whenever you access this, make the call to the database with name and so on, and you have to write this manually, right, for every attribute, because every table is different. So in this way, you can basically avoid all this and produce an interface for your database that the user, the programmer that uses the library can then use, right? This is actually how many of the ORM are built. Let's see. So and then I am assigning basically some methods here. Again, to the class, I'm creating a method load by ID by just referring to its underscore method. I mean, this is not really necessary. You could have just write this, but just to show you how we can create structure in the class dynamically. Right? You can create methods, you can create attributes directly in this in its subclasses. So what we're doing here is we are intercepting the life cycle of the class. We are modifying it with code. So we are what we call this meta programming. We are programming code that generates code. Right? So the rest is basically simple implementation in database connection, and we have load by ID. So the idea is we have a user in database as ID 5. We want to load it from the database. Well, that's simple. We pass the ID, we create a cursor, we execute a select. So we select everything from the table where this ID is 5, right? And then we go, we fetch the first row, and then we go, if there is a first row, then basically we create a user object, right? I use this variable class, which contains the subclass that I'm working with, right? If it's an object if it's a user is user, if it's company, and so on and so forth. I create the user object, and then I go through the attributes and set each attribute to the value that I found in the setup. And then I return the object. And if there is no row, I return none. So the user knows that we're loading by ID 5, there is no user. Okay? If I create a new object, I just do the same as this. Object is equal to class. And then I just, I have some keyword arguments. So I can actually go through the keyword arguments and set the values to the keyword argument. So for example, if I pass user name equal Alice, then this will set the name to Alice. This is not yet saved in database, right? So I need this method save that basically then goes through a certain number of things. First of all, it checks if it has an ID, and if the ID is not known. This is important because if the ID is known, it means that the object has been never saved in the database. Because the ID is returned by the database, right? If the ID is not known, then I can assume that the object is there, and then I update the record. I just go and do update to set these values where the ID is equal to 5. But if it is known, let me go this. But if it is known, then I actually do an insert. Right? So here I have the update, here the ID insert. The rest is just details about how to read the attributes values and put them in the script, but they're not really so important. What important is this save method basically hides from you all the complexity of saving into the database into a method, and when you're dealing with this, you can just use this format here. You want new user, let's create a new user, Alice, age 25, we save it, we print the ID and the name, then we change the name to Bob, and we save it again. I mean, this is just all saved to the database. And we can load the same user using the ID of new user into another object and check that the name has actually changed to Bob. And this all works. And then we deleted everything and so on. So if we run it, you see that first we print the ID 31 and name Alice, then we change it to Bob. We save it to the database, we reload it back from the database using the ID 31, and then we print the name, and then it's Bob. So this is a lot simpler than writing insert from, delete, and so on to the database directly, right? Once you have done the basic work, it's completely done for you. Now, the nice thing about this is that this is nothing specific for user. My implementation of user is here, right? It's very simple. It's just class user pass, done. If I have another table, company, the class company pass, done. all the attributes are there, all my methods are there, everything is already there. And that's because I intercepted the init subclasses and I took care of it there. Any question? Okay, so meta classes. Type is the prototype of a meta class. It's a class that generates classes, right? And meta classes are extension of type. So if you want to intercept the class lifecycle, you can implement it using a meta class. There you can, for example, intercept new. You can intercept the creation of class before a class is allocated in memory. Or you can, if the init subclasses is not enough for what you want to do, you can intercept the init and control completely the initialization of the class itself, not of the object, of the class, right? And so on. Why are this useful? Usually are useful if you write libraries. So if you want, for example, that every class that has been created in a certain way to be registered in a certain internal memory database that you use for housekeeping, you can do this with the meta classes. If you want to enforce standards, for example, you want to control that all the classes have the hints for the variable type because you have a specific use case, so you are bridging to a strongly typed language, you can do that. You can do resource management in there. And also, as we saw, you can do dynamic class creation. We did dynamic attributes creation and methods creation. We can even do dynamic class creation. So we'll see now another demo, basically of switch the same ORM. And in this case, my concern is that if you create the class user, but there is no table user in the database, then I run into all sorts of errors. And I want to catch this before it actually happens. So what I can do is, in the initialization of the subclass, I could check if the table is there. But if I am in the initialization of the subclass, the class has been already created, right? It's been already allocated, some initialization has been already done. Possibly there is a database connection inside. Possibly there are some resources that need to be cleaned up. So instead of doing this, I'm intercepting new. So in this way, I'm checking before the class is even unlocated in memory, I'm checking if the table is there. And if the table is not there, I'm throwing an exception, saying, look, there is no such table, so don't even try, right? Is that clear why I'm doing it? So, and how you do it is actually very simple. If you create a DB object meta, it's an extension of type, and you define new, then you can basically do your database checking here. So what I'm doing is I'm going to check the SQLite master, which is a standard table that contains all the tables as rows, the definition of the tables. And I'm just checking if the name of my class is, name is, to use this, otherwise people often don't really follow. Name is this, right? And it's passed, and I didn't say that. This is passed automatically by Python. When new is called, it will pass to you the name of the class that's been generated. It will pass to you the basis, which means the superclasses. This is a collection of superclasses. Like if your class user is 10, class employee is 10 users, you will have user here and employee here. And then the dictionary of the variable, the class variables that you want. So in our case, this will be empty and this will be empty, but in general, you will have something there. So the name I'm going to check first against DB object, because I will create a class DB object. The object is not in the database, but it will create an exception if I try and look at it up in the database, right? So this applies also to DB object. It applies to all its subclasses, but also to DB objects. So I have to exclude this. And then, if it's DB object, I just return super and let type handle it. But if it's not DB object, then I check. And what do I check for? I check that name is in my database as a regular table. And if it is, everything's fine. If it's not, if table does not exist, raise a value error, and tell the programmer that the table does not exist in the database. Right, and exit. Then no object is created, no class is created, and everything is fine. This is an example, for example, this is an example of how you can register classes in a central registry. So in init, I'm just taking again the name, and I am checking if the name, class name, is not already in a connected table central variable that I have. And if it is not, then I'm just adding it to it, nothing else. I'm just a simple example of how we can use initialization of meta classes to register objects. I'm not running this code because it's just the same as before. Actually, I will, because there you see table name does not exist. So what I'm doing here is I'm checking employee. I didn't have a table employee. And exactly. So I try to define a class employee, and when I try to define it, then it fails with this error message. Table employee does not exist. All right? Any question? Please don't be shy. I mean, this is not a basic Python. So if you have something that you don't understand, tell me and we can discuss it in class. Much more useful than not understand. All right?
So
yeah,
you cannot create another relation or table in the database?
I can, but it was not there.
Okay.
You could, of course, say, well, if somebody creates a class employee, I could handle it by creating a table in the database for him. Right? You can invert the control and say, I define my tables in Python and I create them on demand in the database, instead of creating it first in the database and then in Python. There are frameworks like Django, for example, that use this method. You create your model, you define your model by saying, like in our example, you create a class user, but instead of saying class, you create several. For example, it would be like this: class user, and then you would have like name equal string 50 for length, and then some other variables, and then you would have, I don't know, thinking about age, yeah, and that would be number, and so on. Right? So you define your persistent objects in Python, and then you create what is called a migration, which is a script that reads these classes, generate SQLs for you, and puts it into the database. And then you run these migrations. Every time you change your model, this migration will alter the table to make sure that they correspond to your model. This is one way to handle it. In our case, I took for granted that you do the designing in the database and then you actually look it up from the code. Make sense?
Yes.
Any other question? All right. So there's more you can do with intercepting codes from Python. And in particular, without going into meta classes, there is a simple thing that we'll use again and again, which is called get___. I mean, this, by the way, are called double underscore methods, which are special methods that are used as template methods by Python so that you can override them and do special behavior, right? Double underscore, they are also called dunder methods, or double underscore. Get and set are very important because they give you the possibility to respond to attributes requests dynamically. So instead of init subclasses implementing every attribute from the database into your class directly, you could have implemented this function get attribute and then look up in the table if that attribute exists and dynamically answer the attribute at runtime. Right? It's basically this bread and butter if you want to implement a proxy. Right? You just put everything in the get at and then you dynamically do what is needed. Any question about this? let's look at the demo then. All right. Which is again the ORM. In this case, the logic is all in here. So what I did, I implemented the proxy from the ground up. The proxy has a cache to check if the data is already there. And if it's already there, I just serve it from the cache. So I don't care about the database, but if I already saved before and, for example, the age of Alice in the cache, and somebody asks me what is Alice's age, I'll just serve it from the cache. I'll just return cache get name known. What is this? This is equivalent to cache, in this case would be age, with the difference that if age is not in the dictionary, then it will return known instead of creating an exception, right? This is just a syntactic sugar from Python to do this try, except, and so on. But if it's not there, if it's not there, I first fetch it from the database, right? Check that the result is there and save it in the cache and then return. So this is the implementation of proxy that we saw already, this time with a background that comes coming from the database. So to do this, of course, I cannot scroll from here, of course. To do this, of course, I need to set up initially the cache and a save flag. Well, why do I need a save flag? Anybody can figure it out? I'm basically writing here if this object has to be saved, right? Why? Where would I use it? Do you remember? So I have this object, it's been loaded from the database, and it has values in the cache. Now at some point, I change one of these values. Like for example, I assign the user, which name was Alice, Bob. So I want to keep track if the user has been changed, and if I need to synchronize it to the database, right? This is why I want this flag here. So I have my cache, and I have a flag that tells me if the cache has been masked, it's been changed. So in this case, then I can save it back to the database. And this is what I use then in the set attribute method, double under method, which again, it checks, right? The table is not there, of course. And then if the field is in the table columns, right? So double check. First I check if the table is there, then I check if the column is there. And if both are the case, then then I save in the cache. Sorry, I was confusing with the save. The save here is the same as before. So I save it in the cache, and then I set the set flag to true, right? So now I'm not dealing with the database here. If I change the name to Bob, I'm just putting it in the cache. It's an instantaneous thing, and I'm not saving it yet to the database. Only when I actually code save, which is right here, only then I'm actually dealing with the database. And in this case, it's the same as before. Nothing has changed. I check if the ID is there. If the ID is not there, I do an insert. Otherwise, I do an update. Right? But I also do this so that if you call the save 14 times, just save the database when it's useful. It doesn't, create a useless connection. You might have, a loop where you keep saving the object to the database because you don't want to check. Well, this will check it for you, right? So this is all things that, again, you would use if you write a library for somebody. Let's say you have a sensor, and you want to write a sensor library for somebody that will use your sensor because you are employed, at a sensor producing company. Then you will use some of these techniques. The rest is similar to before. So, you can just run it, and it's doing the right thing as before. Just saving and then reloading it from a new user, and it's still there. All right? Any question about this? Get up, set up. Good. Then let's change topic. So these are some, what I show you so far is some basic way to interact with objects in Python. Now we start looking into concurrency. Why I want to look into concurrency? For several reasons. But first and foremost is because you will use concurrency behind the scene when you use NumPy, when you use TensorFlow, in many aspects. And it's important that you understand what are the underlying problems in concurrency, what are the requirements to implement a concurrent system, and you will need to sometimes explicitly use concurrency when, for example, using cyber-physical system where you have sensor, you have actuators, so you have user interfaces, and then you need to make sure that all these things actually work at the same time, because you cannot just block everything while you're waiting for the camera to give you the next frame, and then process the next frame and then actuate the engine. In the meantime, ignore the camera because you're now actuating the engine, right? So all these things cannot go sequentially. You have to be reactive to different signals, and you have the possibility to control several processes at the same time. So this has brings in with it a lot of problematics that you don't have if you have a single sequential process, and we'll see them one by one. Before we go into parallel processing, as in number crunching, we will look into I/O, which is a bit easier, and it's internally supported by threading, which is a library in Python. So, common scenario in, for example, if you have again a cyber-physical system, you have 3 sensors. This sensor has a bit of lag. Then you read the data from the first sensor. Then you read the data from the second sensor. You read the data from the third sensor. Then you process the data. This is not optimal, right? Because you're waiting maybe half a second for the first, half a second for the second, half a second for the third. So you process the data only after you got through all this processing. But you could wait for this in parallel, right? It would be a lot more efficient if you could do this. Wait for all the servers to respond, and then request the data from everybody, wait for all the servers to respond. When the data has arrived, then you process it. Whatever comes first, you save it in a variable, in a list, in a dictionary, and once you have all 3, you go and process it, right? That's the optimal way to do it. And this is how this is implemented in both cases. Now, this is I'm using here a service which is a commodity service that just responds something like lorem ipsum and so on. Just a filler text so that you can test your code. So I'm just calling this URL 10 times with different IDs, just adding an I that goes from 1 to 10, right? In a loop. So I'm calling it 10 times, and I'm just reading the response, and I'm appending it to my data variable. That's all I'm doing. Clear? I'm using a special way to call HTTP endpoints here that is called requests. It's a library in Python. It's very easy to use, as you see. Just put the URL here, request get, and get the response. As easy as that. How do we parallelize this? So we parallelize it using threads. And to use threads, we first define a function, which is the core that we want to parallelize. Right? The function gets the URL that it should call. It gets a result dictionary. This is a shared variable that it will be updated by the function, adding the results it got, and a key that it should use to update this dictionary. Right? So I have basically a box, right? And I have some ID, 1, 2, 3, 4, and so on. Now I have some threads, right? They are running. I give the ID 1 to this thread. It goes and fetches the data, takes the data back, and then it plugs it back in here. And then I have another thread, and I give it the ID 2, and so on, right? So this is what the thread will run, the central function. So what I do then is I create the infrastructure. I create a dictionary to collect the results. This is just for timing. I start my time so that I know how much time it takes. Then I loop through 1 to 10. And what I do is two things. First, I create the thread. This is just a standard interface, threading thread. I tell it what it should run and what are the variables that it needs to pass to this function. So this is basically the URL. That's first argument. The results is my result dictionary, and the key is response I. Right. So it's a unique key that I can add back to the dictionary. It is passed like this: args equal, and it's passed. What the threading interface then done is this called this fetch URL and pass these arguments to fetch URL, but not in your thread. It does it in a different thread, right? And what you do then is call thread start. Now, thread start doesn't run the thread in your current process. It tells to the other thread, to the other process, to start running that thread. Right? It does that in parallel. So far, so good. All right. So then, what can I do? I mean, I have to know the results, right? And I have to know where they finish it, and so on. So what I do is I do thread join. When I do thread join, what I mean is I'm waiting for that thread to finish, and when it's done, that thread join will be executed and go to the next one. And until then, it will block the execution. So here now I'm waiting for thread 1, then thread 2, then thread 3, and so on. So if thread 1 is done, and then I join thread 2, but the thread 2 is already done before, just go on and go to the third, right? So I'm not waiting sequentially anymore. I'm just checking all of them are finished. So any order is good, because once they're all done, then this will go through, right? And then I check my time. Is it clear? The join clear? This is basically just checking that that thread is finished. If it's not finished, it will wait. It will block the process. So, shall we see that in action? And did I have it somewhere? I don't think I have it. Good. The fact we don't see it in action, I guess. I mean, we could do it right now. But I mean, trust me, it will take more time. Okay. I didn't actually save the file. But yeah, basically what we'll do is that I'll tell you that this will take about 3 to 5 times as much as this. Not 10 times, because of course there is a overhead when you start in a thread, you collect in a thread, you're joining and so on. So this will take basically the longest time of the thread plus the overhead. The longest, the latest thread will be governing time, and plus we'll take the overhead in creating everything and joining everything back. So it will be a little bit longer than just linear scaling, but this will run definitely long. And the more threads, the more requests you have, the more sequential operations you have, the more the parallelization you have. So again, to recapitulate threads. Threads encapsulate the code to be run and can be dispatched in parallel. What pattern was this? Do you remember? Command, right? This is the command pattern in action. You'll see that again and again in multiprocessing. Basically, what you're trying to do is you're putting everything in one block, in one function, and then you dispatch it to a machinery that does the processing for you. This is the command pattern. So the calling process can wait on the thread to finish with join, right? And important, the threads are subject to the GIL, global interpreter lock. So no parallelizing of number crunching. Because whenever one thread is using the interpreter, whenever one thread is executing a line of Python and not waiting on a resource and an answer from the server, for example, then the other threads cannot access the interpreter. This might go away. There's a Python enhancement proposal that has been approved, and it should be implemented in Python, I think 3.13, if I'm not correct, or 3.12, as an option when you start it. Like down minus minus, no interpreter log. Not sure if it's going to be the standard in the future. There's some internal changes that have to be done for Python to be this way, and they have been done. Now it's beta, people are testing it. But it might be that they go back and they start using multiprocessing again. We'll see. But anyway, even if the guild is very important for I/O operations. And most of the cases, also in software physical system, would be I/O. I mean, you have the central processing done in parallel anyway by things like TensorFlow, where you don't have to create multiple processes. You know, you just one process governing 8 GPUs, for example. And then you have a lot of threads looking at resources and dispatching commands, and you're getting data and so on to different hardware, right? This doesn't need CPU, doesn't need a lock on the interpreter. Clear? So again, thread lifecycle. This is your main thread, right? Main process. When you start the thread, this will start processing in parallel to you. And at some point, you might want to join the thread. And at this point, both code have to reach this point before anything else goes on, right? This process must be finished, and your code must have reached the thread join. Whoever reaches that point first waits for the other. That's why it's called join. So, race conditions. Anybody who knows what race conditions are? No. Yeah?
So when some same threads accessing the same block of data or some memory.
Yes.
So
yes.
It's the race condition.
Fantastic. I would give you a star. I don't have them. I have a professor. Back in my days when I was a student, I would throw candies when somebody answered correctly. Anyway, so that's exactly the point. And this is an example of a race condition. It's a very simple program. There is a variable, starts at 0, and there is a function that's called increment. It does 1 million increments and increments the variable by 1. And the other function is decrement, and decrements the value by 1 million times. What I'm doing is I'm starting 2 threads, I'm giving increment to one, decrement to the other. Just starting them in parallel, joining them in the end, and printing the result. Who wants to bet what the result will be? I'm incrementing 1 million times, decrementing 1 million times. The obvious result would be, if I take 0, I had 1 million, and then I remove 1 million, what is the result?
It's 0.
0, right? Yeah. Will it be 0? I will run exactly this code. What do you think? Let's try. So, I'm not cheating, right? This is the same code as before. Increment, decrement, thread start, thread join, print final value. You agree with me? Okay, run. 520, 175. Run it again. 1 million. Run it again. Minus 919. What's going on? Minus 600,043 and 463. Very strange numbers, okay? I mean, I could go on all day. It will always be different. So math is broken. Can anybody explain what's going on? Where is the problem? Where is the bug? One of these lines, there's something not working, right? First of all, where is it? Before we know even what the problem is. What is not working? It is being incremented and decremented, otherwise it would be 0, right? If the shared variable plus equal 1 wouldn't work at all, it will stay at 0. So it will be give by chance the right answer for the wrong reason. But this is actually incrementing the variable, and this is actually decrementing the variable, because otherwise we wouldn't get negative results. So we got both positive and negative results. So they are doing something. But there's something wrong about how they do it. So let's make an example. Let's say you have a bank account, right? And you have 100 euro in your balance. Sorry about that. So you want to withdraw 100 euro. And you gave another card to a friend who also wants to withdraw 100 euro. So let's see what could happen. You do this exactly at the same time, right? So the system, this is your bank account, okay? And it has 100. So you check what the balance is, and it tells you it's 100. Your friend checks what the balance is, and it tells it it's 100. So you withdraw 100, and it goes to 0. He withdraws 100, and it goes to minus 100. But you did check that the balance was sufficient to withdraw, right? And he did check too. But nevertheless, at the end of the day, you got 200 out, and the balance went 100. And that should have been possible, because the system checked the balance and returned the money only when it saw that the balance was there. But what is the problem here?
The latency of the synchronization.
Could be, but in general, it's not just the latency. This could be very, very fast. But if you are very unlucky, very, very fast will not help you. The problem is that these two operations should never run separated by another operation. These two operations should be what we call atomic. So that I check the balance and I withdraw in one single execution, I mean, not one single execution, but in one uninterrupted execution on my CPU. Nobody else can accept that CPU and that data while I'm doing this, right? Because otherwise this can happen. And now let's go back to this problem. What is happening here? What is happening here? Unpack this operation. What am I doing? Shared variables. I'll write this as V, okay, so that you can actually read it. Shared variable is equal to shared variable plus 1. Or otherwise, you could, unpack it even further. A is equal to shared variable. This is a local memory that I'm saving. And then I'm doing assigning to shared variable back A plus 1. Now, if this is done in the other thread, like this, and then shared variable is equal to A minus 1, you see where the problem is, right? Now they have both the same value. The first one will write, they start with 5. First one will write 6, the other will write 4. And so it doesn't work. Right? So this is first time you see it, you think I broke the computer, but it's not. I mean, this is just because this is not an atomic operation. And that's why it doesn't work. So how do we fix it? I'll show you the machinery to fix it, but I want to see if if you have an intuition for what's going on. What could we do to fix this?
Lock it.
Exactly. So we can create a variable that it's basically something like a token that you take and say, I'm changing now the variables, right? And when you're done, you release the token and somebody else will take it and can change it, right? So this is what a lock is. And basically what lock does is that you can define a lock, you can acquire it and release it, and what it makes sure is that only one thread at a time can acquire that lock. So with that, you can basically protect any piece of code you want. If you know that two pieces of code are accessing the same shared information, whenever you access that shared information, you acquire and release the lock, and then you're sure that it's thread safe. Make sense? So this is the typical process: acquire lock, update the shared variable, and release the lock. Problem. This is it's not my idea, it's been in the literature for a long time. The dining philosopher's problem, right? You have 5 philosophers, or any number of philosophers, and they need each 2 forks to eat. I mean, let's leave alone the problem of hygiene, but this is this is an hypothetical abstract problem. Okay, they need 2 forks to eat each. So only certain number of philosophers can eat at the same time because they share a fork with the next philosopher, and they need both, right? So what happens is that they are very animals of habit, so they all start with the right fork, and then they pick up the left fork. What can happen?
Nobody can eat.
Nobody can eat because they all have a right fork in the hand, but the left fork is gone. Right? So this is a very simple example, something that we call a deadlock. Let's suppose that these are not philosopher and forks, but these are actually accounts in a bank, right? And these are transactions. So account A wants to send money to account B. Account B wants to send money to account C. Account C wants to send money to account D, and so on, until we go back to account A. Now, everybody takes a lock on the account because we don't want to screw up the balance like we did last time. So we take a lock on the source account. Then we take a lock on the destination account, but the destination account is not there. It's been locked already by somebody else. So you have a circular reference, and you cannot get away of that circular reference. I mean, the banking system is stuck until somebody shuts it down and starts again. Any idea how to solve this problem? What could we do to break this problem? I mean, at code level, right? How can we organize our code so that these resources are not acquired in this particular way? Like basically avoid this. Tell you a few ideas. Say we give a number to the forks. This is fork 1, fork 2, fork 3, fork 4, fork 5. Now I tell the philosophers that they should always start with the lowest numbered fork. So basically, this philosopher will get 1, this philosopher will get 2, this philosopher will get 3, this philosopher will get 4, but this philosopher will also try to acquire 1. Now, there's 2 cases. Either he can or he cannot. If he cannot, then he will wait on 1 until it's free. And 5 is free, so this philosopher will acquire 5, eat, then release both 5 and 4, then this philosopher will acquire 4, and so on. Right? If he can, then they will contend for 5. 1 will get it, 1 will eat. The other will wait. Right? So this solves the deadlock. Is it efficient? Consider you have 100 philosophers. What will happen is that they eat in sequence, right? So it's not efficient. What can we do to solve the efficiency problem? Any idea? One possibility would be that at random, a philosopher decides, since I cannot take the second fork, just drop the first fork as well and try again in a few seconds. Right? So back off from the resources. This could work. And actually, it would allow the other process to take the fork, finish its task, and then release both. And then when you try again, it might actually be there. Right? But it introduces a certain latency. You could even do something more complex. And ask nicely to the other philosopher to please give you the second fork, because you have the first and you're waiting to eat, and he doesn't do anything with the second fork. So if you ask nicely, maybe he'll give you the second fork. So these are contention resolution systems. There's several ways to implement this, but it's important that you're aware that this is a problem. And I mean, the details you can look into concurrent programming books. So there's even cases in which you say, you know what, I'll let everybody take whatever resources they want, and then I'll clean the mess later. Like if you change the bank balance, I'll let you do all the operations, and once you have finished the operation, I create a command, and I'll check the command against a validation system. I'll encapsulate all of the operations that you want to do, then I'll validate it the second time. Right? So this basically gives you the ability to manipulate the system, and if there is a problem, I catch it later, and so on. So there's very multiple ways to do this, but in general, it's enough to be aware of the problem and know that when something is not working, it might actually be for a deadlock. Because if you have shared resources in your system and you try to acquire it in a strange way, this would happen. And these are the worst problem to have, because they are very hard to debug. They happen once in a while. Absolutely no reason, just coincidence, and then they lock up your system. You cannot debug it. You have to turn it off, and then when you turn it off and test it, it will always work. Because when you test it, the timing is different than when it's actually on the machine, right? Because the latency that you have in test is actually less or more, depending. And you never encounter this thing. And then when it's deployed on the production system or on the machine, on the robot, whatever that is, that might run millions of times. And it might happen one time in a million. But if it runs millions of times every day, then you have to lock up your system every day, right? So deadlocks. Be aware and be wary. How can we avoid all this? Instead of using shared resources, we can actually use communication frameworks and communication infrastructure that are already trade safe. And there's a few things that Python offers. Just talking about two today. The first is a condition. Actually, first is a queue that basically allows you to queue some information into this queue, and somebody else can listen to this queue and get this information. This will not put any unsafe variables that are shared in between the two threads, because one is writing, the other is reading. There is no contention. And there is a special queue that is called condition that allows you to send notify for events. And there's a bit of machinery behind the scenes that allows you to use shared variables safely. And at the same time, this is done for you behind the scenes, basically. So we'll see an example of that. So we have a consumer and a producer. This is something that you'll see a lot in programming, in parallel programming. A producer will just basically generate jobs for the consumer, will send data, will retrieve camera videos, will generate actions for an actuators. And the consumer is there waiting for it, and then processing whatever it gets, right? So in this case, we use a condition. And the interesting fact about this condition is that when you enter the context manager, like with condition, this is a typical context manager, like with file, right? With file open as F. This condition has an internal lock, and it will lock this internal lock, so that these two with conditions cannot operate at the same time. So it's a lock behind the scene. But it has a special method, condition wait, that will release that lock. So, for example, in this case, you are checking that an item has been sent to you, right? Item is this global variable. If the item is known, I wait, and I give the producer time to produce the item. And then I check again. Here, when I'm here and I'm checking item is known, I am locked, I'm thread safe. But when I'm here, I'm not. But I don't care because I'm waiting, right? So the producer has only to do one thing. use the condition, produce the item, and then notify. When it does notify, then this condition wait will actually release and go back to the check. So the notify will trigger the condition to get out of the waiting, right? So it's a very friendly machinery to have a shared variable and pass events so that I don't have to continuously check for the value, but just wait for the producer to tell me when I should check. Make sense? All right, and so you can do the same with queues, and it's actually simpler. I just wanted to show you both functionalities. So with queue is even simpler. You define a queue, and basically on one side, you put something in the queue, and on the other side, you receive it. Queue get. This queue get blocks the process until you get something. So it's very, very, very easy. And this is the best way, unless you have really large data, this is always the best way to synchronize threads. Use queues, pass messages from one to the other, and so on. I mean, if you have, of course, an array of images of 3 terabytes, you don't want to put it in a queue, duplicate it in memory, and read it from the other side. Then you want to have the shared object. You should take care of using all the locks and so on. But if you have simple data, use a queue. It's the simplest way to synchronize the threads. Questions about this? Right? So, what can we say here more? Yeah, one thing that you could do is actually, advertise the fact that you finished processing the queue, but not really. That's the important part. So, how do we use all this machinery to get things done? Typical case, you have a certain numbers of computation to do in parallel. You want to distribute it amongst threads or servers to collect data from it. A more apt example, since we cannot use CPU prioritization with threads. So you have several servers you want to collect data from. What you can do is what you did before. You can create a function that actually collects the data, and then you have a queue. You start each thread with this function, and you put it in a loop. This thread will wait on the queue. Whenever it receives the URL, it will fetch the data, return you the data, and then wait again on the queue until it finds the next message. They share one queue, so you just pipeline all your requests there, and each worker will pick up the next request that it gets, get the data for you, put it back in the pipeline for you, and then wait again for the next request. So you can parallelize this fetching over many workers. Make sense? Right? Another couple of machineries that you will encounter, semaphores. Semaphores are lock which allow multiple threads to acquire it, but can limit the maximum amount of threads that can acquire it. These are used usually for something like being nice to the system. For example, like if you don't want to overload the database, you might put a semaphore in there so that not too many processes can actually talk to the database at the same time. Or if you want to make sure that your program doesn't run wild with threads, because you can create threads on demand and then just have thousands and thousands of threads, creating then a problem to interpret. So you can use a semaphore for this. There is one very important use for a semaphore, which is a read-write lock. And the read-write lock is a very important one, and you will find it if you use shared memory when you do, for example, share a large array. Why? Let's say you have a process that is reading from an image, line by line. You could actually parallelize this and say, okay, I read the first 5 lines with one process, the second 5 lines with another process, and so on and so forth. They don't have any contention there. It's just reading, right? So you can make the readers access the array completely independent of one another without locking the resource. But you must make sure that when the writer accesses the array, like when you're changing the image with the new image, that all the readers are stopped, because otherwise you can get inconsistent data when you look at what the reader says processed. Make sense? Right? So to do this, you can implement this. There is no such lock in Python standard library, but you can implement this easily with basically one lock and one semaphore, right? So what's the idea? The idea is that the writer has a lock, and when it acquires it, nothing else happens. But when the writer releases the lock, the readers can acquire a writer lock common to everybody, and then increment the semaphore. So when the semaphore goes up, nothing happens. When the semaphore reaches 0, the writer lock is released. Right? So what I check is if the semaphore is count 1, I acquire the writer lock. If the semaphore is gone down to 0, I release the writer lock. In this way, the writer can only have access when no reader is active and vice versa. And no reader can access the array when the writer is active. Is that clear how the mechanism works? So, add an example of this. And this is here. So, in implementation is quite simple. So I first set up my my basic variables, a semaphore, a lock, and a count, right? So then, when I acquire read, what I do is I go through the context manager of the semaphore, right? And then I increment my readers. And then if the readers is equal to 1, I acquire the write lock. Right? So the first reader locks the writer out. The second doesn't need to do it. The second would not be able to acquire the writer lock because the first reader is. Right? When I release read, I acquire the reader semaphore. Right? But I can acquire multiple reader semaphore. This is not a problem. Right? But when I do this, I decrement the readers. And then if the readers is 0, I release the write lock. So when no reader is there anymore, then the writer lock is free again. So now, the writer just need to try to acquire the write lock, nothing else. Make sense? So, and this, since we are at it and we're using Context Manager a lot, to support with, so that we can actually write with the, our read write lock. You can actually do it like this. You can use this decorator, context lib context manager, and then basically define yourself what happens with that context manager. What this block of code does is basically insert whatever is under with. So this part of code, it goes and inserts it here. Right? So when you use with read write lock or read lock in this case, we'll basically do the acquire of the read lock. Then we will try, execute your code, and then finally release the lock. Right? So you can support context managers in your own code. Same goes for the write lock. Same structure. And then see what I did there. Yeah. So now, once we have this, I can define my reader with read lock, do my reading, and then printing down. As simple as that. Writer lock, the same. Just printing writer lock is waiting so that we know that it actually there. And then once it gets the lock, we will print is writing, sleep for 1 second, and then when I print down. Right? So if we run this with 3 threads, you will see that the reading is done in parallel, but the writing is waiting. So, have you seen? Reader is reading, reader 2 is reading, then it was waiting for a bit, writer was waiting as well, then reader 1 is done, reader 2 is done, and then the writer acquired the lock finally and could write. So this is, again, this is important when you have shared resources where you have somebody that updates the resources. For example, a camera process is taking the image, is update the image, Then you have several processes that look, for example, you have a hedge filter, you have a RGB convolutional neural network, you have something really in the depth, different channels, different things, they can read and do this in parallel. But when the camera is updating the image, you want to stop all that and update the image, right? So, questions? All right, so let's move on. Oh, actually, that is it. So, if you have any questions, we can discuss them now, even about the last week. We still have 15 minutes. Otherwise, we close it early, and I will update the course to accept you and everybody else who is not accepted and wrote me an email. You wrote me an email, right? About the waiting list.
Yeah.
Okay, so yeah, I'll then accept everybody who wrote me an email into the course. Good. Start the registration.